to introduce Professor J. Rosen. Jay received his bachelor degree in mathematics from Harvard University in 1970, yes, and the PhD in mathematics from Princeton University in 1974. He was a research associate at Rochester University in 1974 and stayed there for 2 years. He became an assistant professor in 1976 and promoted to associate professor in 1982. Both happened at the University of Massachusetts. He moved to the City University of New York as a professor in 1986 and stayed there since then. Jay is a fellow of the IMS and an associate editor for the Annals of Probability from 1997 to 1998. He was invited to present lectures in a number of conferences and workshops. Jay will talk about the law of iterated logarithm for permanental processes and the local times of associated Markov processes. Jay, the screen is yours.
Okay, I think you can see the slides, I hope, by now.
Yep.
So this is joint work with Michael Marcus. And I start from, whoops, why doesn't this? Okay. So we have a Markov process called x sub t. In some state space, you can think of it as the real line or some subset of the real line. That's what we'll be dealing with mostly. And it has transition densities, pt of xy, which means that when you calculate the expectation, you get it in terms of pt. Now, one second, I'm surprised. Ah, it works now. Once you have the transition densities, by the way, I should, with respect to some reference measure, dm. Once you have that, you can define the potential densities. This is the integral over t. In the first case, you can call this the zero potential density. This makes sense when the process is transient. And for our work, we're going to deal with transient processes. But if not, we have the alpha potential densities. This is obtained by killing the process, original process, at some exponential time. Now, I begin with symmetric Markov process. So the transition density is symmetric, and I want to show it's actually positive definite. So here's the proof. You write out the expression for, you want to show this is positive, and then the transition density, you write out in terms of the Chapman-Kolmogorov expression here. And now, by symmetry, in the second factor, I could switch the xj with the z. And then this whole thing becomes a square, and so it's positive. So pt is symmetric and positive definite. And furthermore, the potential is symmetric and positive definite. And as you know, if you have a function that's symmetric and positive definite, it's the covariance of a Gaussian process. So we say the Gaussian process, g sub x, whose covariance is this potential density, we say it's associated with the Markov process x. Okay, what good is that? Well, we define for the Markov process the local time at some little x. This is an approximate f epsilon x is an approximate delta function. So you should think of this as the amount of time the process spends at x up till time t. And it's well known that for Brownian motion, this local time is continuous. It's jointly continuous, but it's continuous especially in x. And for a long time, people knew Brownian motion and some variations of that, but then Michael Marcus and I proved the following theorem, that the local time is continuous if and only if the associated Gaussian process is continuous. Now, at first glance, this just seems to be that we've taken one abstract question, when is the local time continuous, and we replaced it with another abstract condition. However, Gaussian processes are well known. And we have a necessary and sufficient condition in terms of the, well, it's in terms of the covariance here. This is, BD is the ball, where you use the metric is the incremental standard deviation here for the process. And this would be the ball centered at S of radius V. So this is a result that was worked on for by many mathematicians, and the final version is due to Talleyrand. So how did we get this? So this is the result that I mentioned, the if and only if. This is the result that Michael Marcus and I obtained in well, we both came, you heard, I came in '86 to City University, and he also came at that time. And I was interested in local times, and he was an expert in Markov processes. And we were able to put this together because of the following, what's called the Dynkin Isomorphism Theorem. It relates the local time, this is the total local time of the Markov process with the associated Gaussian process. I've put different colors here to emphasize that in this theorem, the L, the local time, and the Gaussian are independent. They have their own measures. They're independent of each other. Also, notice that this is not what we usually call an isomorphism theorem, where one side would have something about the Gaussians and the other side would just have something about the local times. It's more complicated and there's more work involved. I'll come back in a minute. This measure here is a H transform. It's essentially telling you, you look at the process started at X. Well, here I started at Z. And it's conditioned, zeta is the death time. We have a transient process. It's conditioned so it dies at X. So you start at Z, you do whatever you want, until at the death time you end up at X. So let me go back again. So on the one hand, officially this is just with respect to some countable set of xi's, but let's just think about this as f being an indicator function saying that this process is continuous. So if I know the Gaussian process is continuous, so the squares are continuous, then it's with probability 1, then it tells me that the sum of the Gaussian process and the local time is continuous, almost surely. And that's great because since G is continuous and the sum is continuous, that shows the local time is continuous in X. The other direction is much more complicated because imagine, let's say I knew that the Gaussian process was discontinuous with probability 1. Then the sum of the local time and the Gaussian process would be discontinuous almost surely, but that might simply be because the Gaussian part was discontinuous. So to show that if the Gaussian is discontinuous, the local time is also discontinuous. This is a more complicated story. I can just point out, make a plug for my book with Michael Marcus. I don't know if you could read it here, but it's Markov processes, Gaussian processes, and local times. And this is the sort of stuff we deal with there. So I'm still, this is all background to what I'm really, the new work. So now I want to talk about laws of the iterated logarithm. So let's say we have a Gaussian process with the covariance, as we said, and suppose that for some function phi of t and some d, we have this sort of LIL. And I want to show how this will get us an LIL for the associated local times. So now I'm going to see if I can do this. I want to go to my board. So stop share. I'm going to try this. And now video here. Yes, so I hope you see the screen. So let me know if this is not clear, but so we want to look at, we have g at d plus x squared, so always divided by 2, minus g at d squared, something divided by 2, over whatever square root I had, 2, 3 of x, log 1 over x, and I'm looking at the limit so as x goes down to 0. And the point is, I factor this difference of 2 squares as, so this gets factored, different color. This becomes g of d plus x minus g. Can you see up there? Is it okay? G of d times the sum. Oops. This is not the sum. G plus x. And divided by 2. Now, in the limit, we're dealing with a continuous process. So this converges to g of d. And the difference divided by that converges to 1. That was my assumption. So this is going to end up being g of d. Really work interested in absolute values. Absolute values. Okay, now I go back to my slides. And now share. Okay, so given the bottom line there, what we've shown is that for the Gaussian square, you get, well, I rewrote this absolute value of GD this way because I want to, this is what comes up in the Dynkin isomorphism theorem, and therefore we have the following. Since the Gaussian squared had that property almost surely, the same thing holds when you replace the Gaussians, well, by Gaussian plus local time. Okay, now what happens here? How do you get rid? I want to get rid of these Gaussians. Then I'll have an LIL for the local times. But on the one hand, a Gaussian, well, as I've emphasized, especially by the colors, the Gaussian and the local times are totally independent. You could even think of them as living on separate sample spaces. So we pick a point in the sample space for the Gaussians where we fix an epsilon where this is less than epsilon. That set has positive probability, as you know. So this thing is less than epsilon, epsilon squared. And this when you divide by that, we already know that that converges by itself to g of d. So this part also is less than epsilon, and you could just get rid of it. So we can eliminate the g's here, and we're left with the LIL for the local times. So this is the basic background. Here I spell it out. We get this LIL almost surely. Now this is the total local time. Using properties of local times, you can then get it for, as we have here, almost every t, up till the death time. Why can't I have it at the death time? Because as I mentioned, the measure QVV is forcing you to die at a certain point, and so you can't, in general, you can't know what happens actually at the death point. Okay, so this is for the case, this is all background. This is for the case that the Markov process was symmetric, so we have the Dynkin isomorphism theorem. The big question for us, and for people who've worked in this, was what happens if the Markov process is not symmetric? So the background to the answer, I want to look at the Laplace transform of a vector, an n-dimensional vector of the g's, gx1 up through gxn. And I take this matrix, n by n matrix, uij, and S is a diagonal matrix which corresponds to the numbers here, S1 through Sn. And let's just calculate that matrix. Well, the density of a Gaussian is given by this. If the covariance is U, this is U inverse. This expression here gets translated into that for the inner product for Rn. Now put these two together, put the two exponents together and do the integration. You pull down the U inverse plus S to the 1/2. Multiplied by that, you get this expression. So for a Gaussian square, a vector of Gaussian squares, we get this expression for the Laplace transform. And now we have a new definition. If you give me any n by n matrix and diagonals, then if I can find a vector xi's such that this happens, then the xi's are called an alpha-permanental vector. In our case, we're mostly concerned with 1/2, but this is quite general. This is called the kernel. And I want to mention that such random variables were first studied by David Vere-Jones, who probably some of you know. He's in New Zealand. This paper in 1997 was the New Zealand Journal of Mathematics. So he was the one who first studied these types of random variables. He called them generalized gamma random variables. And the question would be when, first question, when do such vectors exist? And more generally, if I have a stochastic process, say x sub s, we call it alpha-permanental process if for any finite dimensional subset, you get a permanental vector. So, whoops, I'm sorry. Yeah. So this is a theorem that's due to Eisenbaum, Natalie Eisenbaum and Kaspi. It says that if you give me any U, which is the potential density of a transient Markov process, then there always exists an alpha-permanental process with that kernel. And we call that the permanental process associated to the Markov process Y. And stare at this a moment, because the next slide says that there was no condition there of symmetry. So if you have any Markov process, basically, with a nice potential, then you can find alpha permanental processes with the kernel U. In particular, the x1/2, alpha half, it doesn't have to be a Gaussian square. So this is something new. And amazingly, Eisenbaum and Kaspi show that there is an isomorphism theorem that relates just like the Dynkin isomorphism theorem. In fact, it gives you the Dynkin in the case where alpha is a half and the x are by a Gaussian squares. But we have a general result here. And consequently, we could start playing the same games to try to find, first of all, necessary and sufficient conditions for the continuity of the local time. And what I'm going to talk about are in terms of laws of the iterated logarithm. So the first thing to point out is that it's easy, just like with the Gaussians, to show that if the permanental process is continuous, then the local times will be continuous also. However, as opposed to Gaussians where so much is known, we do not have necessary and sufficient conditions for when a permanental process is continuous. Michael and I have some, we think, pretty good sufficient conditions, which in the Gaussian case would be the necessary and sufficient, but we don't know that they're necessary and sufficient. And more importantly, we can't go backwards. We can't say that if the local time, that if the permanental is discontinuous, that the local time is discontinuous. So this is a big open question. Find necessary and sufficient conditions for local times of non-symmetric Markov processes. I know people like Kaspi used to say that now she's retired, but she was going to wait to retire until somebody solves this problem. But it has not, it's still an open problem. But we're going to focus on the question of laws of the iterated logarithm. And basically, I'm going to give many examples, general examples, but of course, just like we can't show continuity, we can't show in general, we don't know how to show that there are LILs. So this was our goal here, as I put it. There's some function such that I have an LIL of this form, and in particular, think of alpha to be 1/2. That's easy to work with. So we had this in Gaussian squares for very, very general Gaussian processes. A huge amount is known, whereas here, this is something new. And that's what we want to talk about. And what we're going to do is we're going to start off with a symmetric Markov process. All right, it's a little fancy Borel-Wright process, but a symmetric transient process with continuous potential densities. And we're going to perturb it. And here's the perturbation that we're going to work with. So the symmetric has uxy as its potential. And what we do is, what we're going to say, and I'm going to show this later on, I'm going to show why this is true. If you have any finite excessive function for the symmetric process, then if you add that to the potential, this u sub f is the kernel of an alpha permanental process for any alpha. So this is clearly not symmetric anymore. By adding the fy, you've broken the symmetry. And however, you're starting with a symmetric process. And so we're going to have ways to work with this perturbed new process. So I'm going to come back later to explain where this comes from. But first, let me just remind you what it means for excessive function. A function, by the way, it has to be non-negative. I didn't put that in the slide. It's excessive for a Markov process if this holds. And for our purpose, if you're not into this, for our purposes, all I want you to think about are what we call potentials. So you integrate the original potential with respect to some positive measure. That would be excessive. And more specifically, if you take any positive measurable function h and you integrate like that, this will be excessive. And it's, as I said, we call this a potential. And we're going to be working with potentials mostly. Okay, any questions on that? So I want to give several examples that we have, and I'm going to stick to the examples that involve Brownian motion, because that's the most familiar. In fact, in some ways, they're harder than we have a lot of similar results for general Levy process, symmetric Levy process. But we start exponentially killed Brownian motion. This is its density because of the beta here. You can see that the potential density here is really a function of x minus y. And this would be the incremental variance for the associated Gaussian processes. It's basically 2 times x. So we definitely know LILs for this process, but we're going to perturb it. I say k, any integer, but forget, just take k to be 1. There will be a half-permanental process with this perturbation, f of y, where f is a nice excessive function, and it's easy to give many examples. And then we show, based on this, we're going to show that we take any point, and if f prime at d is 0, then we get a LIL for the perturbed permanental process with the same, which would be the same LIL as for the original, the killed Brownian motion, Gaussian squares. This condition, f prime of d, is rather restrictive. We can give many examples. In the case, it's special. I don't know if I have time to explain why, but this is special for things that come from Brownian motion. If I'm dealing with symmetric Levy processes, then I don't need a condition like that. Let me give the next example. Now, I take the original y, so it was exponentially killed Brownian motion, and now I kill that the first time it hits 0. So now this is its potential density. It's no longer a function just of x minus y, or maybe it is. I guess it is. But anyway, the sigma squared, we keep the same one, and we have the same sort of result. That you could perturb it with a nice C2 excessive function, and you get, again, if the function has derivative 0, at d you get again an LIL, which would correspond to the same LIL you would have if you were dealing with the unperturbed symmetric Markov process. One more. Finally. Just take Brownian motion, unkilled, but you kill it the first time it hits 0. Then its potential looks like just the covariance of Brownian motion, but this is what you have. And then the incremental variance is this. And once again, we have the same thing. You could perturb it by an excessive function, and you get an LIL. So this is a sampling of the sort of results we want to get. So first, now I want to go back to explain what's going on. So how do I get this perturbed process? You start off with our symmetric process, and you take a potential of this form. So f of x, you integrate the original potential of y with respect to some measure mu. And we claim, and I want to show you why this is so, we claim that there is a new process, which, however, I have to increase the state space. I have to add another point, star. It's isolated. But with that point, I get a nice Markov process, and its potential densities, well, if you restrict to the original state space, in our case, this was R1 or the positive real numbers. But anyway, if you restrict to that, it looks exactly like what I was talking about, a perturb. And you have some other conditions at the isolated point star. And this is respect to a measure which just gives, it was the original measure and a unit mass at star. So let me try to explain how this works, how this partial rebirthing works. By the way, there are many, in Markov process theory, there are many different examples of rebirthing. This one we found very convenient to use. So let me explain what's going on. So remember, we're starting with a nice Markov process, transient process, which has some death time. And I have a measure mu. Remember, that was the measure that gave rise to my excessive function, my potential f. So my new process, you start in t, and you let it evolve just like the original y until the death time. Then it goes to star. And then, well, it stays there from exponential time. I don't need to think about that now. That relates to the second line of my conditions on the potential. But after star, it returns to t with initial law, which is mu over 1 plus rho. Rho is the mass of mu. What does that mean? Once it returns, it does the same thing over and over and over again. So what does that mean? It starts with initial law mu over 1 plus p. That means that the probability is of this form. Initial law mu means you integrate over all possible d's with respect to mu, and you divide by 1 plus rho. What is the total mass of this probability, though? You could see this is 1, PV of A is 1. So the total mass is the mass of mu, which we said is rho over 1 plus rho. So the total mass, this says that you only have probability of rho over 1 plus rho to be reborn at each step. So now, I'll show you, let's see. Yeah, I want to do this out on the board if I can, because it's very long. Okay, let me stop the sharing and go to my board. No? Yes, there it is. Okay. So let me try to explain now how you get the potential. Erase this. So the potential is of this form. You start at x with the new process. Take some function, any function whatsoever, z of t dt, and you integrate it from 0 to infinity. So that's going to be my potential of my new process. And we want to expand that, if this pen works. First, we do the integral up till the first death time. Then z, as we said, is the same as so 0 to the death time. This is the same as y of t, our original Markov process. And we know the potential of this. I'll write it down. We know exactly what this is. We'll write it down in a minute. And then the next step, it's reborn. So for plus, the second step, it's reborn. with initial measure mu over 1 plus rho. And once again, so here's V. We again let it run according to Y up till its death time. This would be step 2. Now, step 3, what you do is, it's going to look like this, except we've lost, as we said before, it only has probability to get to the second step. So I'm going to add this. The second step with probability rho over 1 plus rho. And you keep on repeating this. Some n goes from 1 to infinity. This would be an expression for the potential of this. And now let's see what we have. This, as I said, this is precisely what we call, so this, oops, doesn't work. Let's try a different color. This is precisely u of x out of y. And what about this? Well, I'm going to first take this sum, oops, together with this. This whole blue thing is 1. Okay. Geometric series. So I'm left with this now. So this thing becomes, what I'm left with is integral d mu v of, this is u, v, u, I'm sorry, I didn't say this right. This is the integral of u x y g of y. G in there. So here, this is going to be the integral now of g, now of v y dy. No, sorry. The integral of u v y g of y dy. Okay. And now we interchange the order of integration, and this integral d u v of u v y, that was exactly the f. That was exactly my new f. So I get, the whole thing here is plus integral of f of y, g of y. So this is the explanation of the partial rebirthing. It shows that we can always get new asymmetric Markov processes by just adding a potential. So let me go back now to, that's the last time I'll be at the board. And share screen. Okay. Let me go ahead now. I have a few more minutes, I guess. So just as we saw for the symmetric case, if using the new isomorphism theorem of Eisenbaum and Kaspi, we can show that if the permanental process has a law of the iterated logarithm, then the local times of that process will also have this type of LIL. Now, if you remember, if I can go back to page 14, let's see. Does that work? Yeah. Remember what happened here was I said that we could ignore the G's because these are Gaussians. They're independent of the local time. And I can find, for any epsilon, I could find a set of positive measure where this is less than epsilon. The permanental process also works because if you think for a moment, the 1/2 permanental process, the marginals, the one-dimensional marginals are Gaussian squares because there's no question of the symmetry of the kernel. It's just UXX. So we have the same story. Back to 45. Okay, so again, I want to pace myself. When shall I end? Can you tell me?
Okay, you have 6 more minutes, please.
Okay, so let me try to get to the heart of matters. I just want to, without, I can't give any proofs because it's very complicated, but I just want to get to the heart of things. An M matrix is a matrix A whose off-diagonal terms are negative and whose inverse is positive. Positive means that all the entries are positive. And the example...
Sorry, you have 10 minutes.
10? Oh, okay.
Sorry. Yeah.
Okay. Okay, so yeah, this is an M matrix, and there's a fact that if we have a matrix whose inverse is an M matrix, then it's the kernel of a permanental vector. Let me give an example of that. This is the case corresponding to Brownian motion killed the first time it hits 0. This would be the potential, twice the infimum. And if you just check things out, you could find the inverse of this is given by, lo and behold, an M matrix. The off-diagonal terms are negative. And in fact, most of the row sums are 0, but that's not important. The main point is that in general, the off-diagonal terms are negative. Here's a general case. This corresponds, I have my original U. This is, I take at particular points the U corresponding to my original symmetric matrix, and I perturbed it by some F. And one can show that this automatically is a inverse, the inverse is an M matrix. Well, I made it look like an M matrix, but are the V's positive? Are the V's non-negative? Let me explain why it has to be, and this is why we take F to be a excessive function of potential. Intuitively, take the case where F was, I write it intuitively, this is the integral of U x y of h of x. And then V, remember, was U inverse of that. So formally, it's H, which is positive. In fact, it's a little more complicated because here I'm not taking the inverse of it. Uij is the inverse matrix, but this is not the same as integrating over all possible things, but the same, one can show that if F is excessive for the original process, the V's and the R's will always be non-negative. So we do have a nice permanental process. And then we symmetrize that. U itself was symmetric. We symmetrize it by, we had here, on the first row we had the V's, and the first column we had the R's. So we take the square root and we symmetrize that. This guarantees that the inverse of that will be a nice symmetric kernel, therefore a Gaussian covariance. So the main technical tool in our approach is the following comparison theorem. Z is the, again, take alpha to be half, but the Z sub M, I have that, it's the alpha, 1/2, or the alpha permanental process corresponding to those M points. And the Z tilde is also the Gaussian process whose covariance was given by the symmetrized version. And now there are two things that we have to do to get our result. We have to show that as m gets larger and larger, so what we're looking at is an LIL, so we're looking at points converging to some point D, so we get more and more points. As m gets larger and larger, we have to show that this goes to 1. So that's first technical difficulty. Once this goes to 1, then you see that, in some sense, the two processes, the symmetrized version and the Permanental version that we're interested in, will then basically have the same probability, approximately the same probability. So the second technical part is to show that with this new symmetrized version, symmetrized Gaussian process, to show that that itself has the same LIL as the original symmetric process we started with. So those are the two technical points. And if I have another two minutes, all this, however, refers to the lower bound in the LIL. That's really the hard part of everything, because I'm just looking at sequences. I'm not looking at the whole picture. The upper bound is also technical, but it's in some ways easier. There's a quite general theorem that says that for any alpha Permanental process with such a kernel, you take its square root, the x is always positive. It's a Subgaussian process. I'll explain in a minute what that means. With respect to the metric, if you look at this metric, if U was symmetric, this would be -2 UST. This would be the covariant, this would be the incremental variance for the original Gaussian process. But now, my U's are not necessarily symmetric. And what this means is the following, that you take the alphas, you have the same sort of exponential bound as you have for Gaussians. And so many things come from using Borel-Cantel lemmas, etc., using this bound on the Gaussians. So using a similar thing here, we can get all sorts of upper bounds. Okay, I think I'm going to stop here. That's my, the rest is more technical. All right, thank you for the invitation.
Okay, thank you very much. Questions, comments, please, plenty of time. Jay gave us plenty of time to ask questions, so we can ask many questions.
I hope there'll be many answers, but okay.
If you have questions, then you can unmute yourself and direct ask your questions. All right. If no questions or comments,
well, I have a question. Sorry, Ewa,
yeah, okay,
I have a
good.
question.
Please.
Yeah, I was
please.
trying, but I was pushing the space bar and it was just making spaces in like a different application. Anyway. So I don't know much about these alpha Permanental point processes. So you showed us one nice property involving this law of the iterated logarithm. But like, can you just say a few? I don't know. Are there basic examples that we might be familiar with, or what kinds of other properties do people know about them? Like more basic path properties or something like that.
Well, continuity was is for us a big issue, because that would lead to continuity for the local times of the Markov process. And as I sort of mentioned, we have good sufficient conditions for continuity. And we have various papers trying to give various necessary conditions, but we can't put that together. We don't have necessary and sufficient conditions. Let's see, what else? That's basically what we've been working on: continuity, LILs.
I mean, so I guess like, implicitly you can read off like the finite dimensional distributions from that expression of the Laplace transform you had, right? So, But it's sort of an abstract, defining something with like the Laplace transform isn't the easiest thing to understand. So, I mean, are there other outside of Gaussian processes in the case where you're defining it based on a symmetric transition kernel? Like, are there other examples where, you kind of get a process that's like, oh, this is like an old friend or something like
that? I don't know. David Vere-Jones has various examples. The one-dimensional things are gamma random variables, but other than that, I can't say they're old friends. These are new friends that we're trying to understand.
Okay, thank you.
I mean, they are defined by a kernel, but in terms of the Laplace transform. Okay, hope you have a good flight.
Thanks.
Any other questions, comments? All right, no questions, comments. Then in that case, let's thank Jay for the intro talk. Thank you, Jay.
Thank you.
Thank you for that. All right, okay.